Hello, my name is Mikhail Davydov. I'm head of SDET practice in InRhythm, and today we'll talk about test design and in particular how to approach design of the test data. As many of you know, it is really hard to find all the defects in any meaningfully complex piece of software. In fact, in most cases, it is simply not feasible. And because of that, it is very important how we approach test design, and in particular, how we select our test data to ensure that all the meaningful scenarios that the real user can encounter while working with our software are covered. There are two main approaches to software testing. They are traditionally called black box and white box or glass box testing. Black box testing is a type of testing that is usually practiced by QA engineers, and it assumes that we know very little about the system. However, what we do know is how the system is supposed to work, so that when we feed the system, consider it to be a black box with particular data, input data, it produces the outputs that we expected to produce. And the goal of testing in this case is actually to validate that it is the case, that when we put certain inputs into the system, that the system produces the outputs that we expected to produce. So in this case, we don't have to know how the system works, what is inside that black box. It is a high-level testing, and it's very well suitable for end-to-end testing. And usually it is based on some kind of a specification or requirements document. The other approach is called glass box testing, and it assumes that we know very well how system works. We know which modules it consists of. We know how those modules interact with each other. We know which data structures are being used. And this is how developers do the testing. And the best example of our glass box or white box testing is unit testing. In the case of the white box testing or structural testing, we can cover all or most of the code passes of the instructions that our program consists of. And this way we can achieve the very high coverage. However, in case of white box testing, we are validating that the program behaves how it is programmed to behave. So basically that we understand correctly what how we programmed it to behave. But we don't test that it is valid for the purpose. We're not testing that it matches expectation of the user. This is what we are doing with a black box testing, and that is what we will be doing today. The other way to look at the software testing and the different types of software testing is how we view the system in terms of how we decompose it to understand which test cases we need to implement. So we can view the system as a set of different smaller parts, smaller functions. Each of those functions accept certain inputs and produces certain outputs. And this is how we will approach the testing today. The other approach is to view the system from perspective how the user interacts with it. And when user interacts with the system transition from one state to another. And in this case, the goal of testing is to cover all those different states in which system may exist, and all those possible transitions. And a good example of this kind of testing of our test design is when we design tests based on the UML or use case diagrams. And it is better suited for designing bigger test cases or trying to ensure the test coverage of the entire system and designing test plans. Again, today we will be talking about designing individual test cases, so we are seeing the system as a set of small functions. We'll talk about a handful or even less pretty basic techniques used for a test data design. In particular, we will talk about class equivalence partitioning, boundary value analysis, and about using special values in testing. So first, we will talk about what those techniques are, and then we will walk through a couple of examples. So first of all, let's talk about classes of equivalence. When we think about classes of equivalence and how they are applied to software testing, we are trying to find the particular classes of test data that produces the same outputs. So some particular set of inputs that produce the same outputs. And for the needs of testing, we're saying, okay, we can take any of those test data, any of those input values and for testing, because any of those will produce the same result. And in this case, the first thing we do when we look at the piece of software, we're trying to understand which different results or types of results it can produce. And we try to find the particular classes of equivalence for each of those classes of outputs. This is a pretty robust technique and pretty powerful, but it disregards the fact that a lot of bugs happen when we are using the data that is on the boundary between two or more classes of equivalence. This is where most of the defects can be found. So imagine, for instance, that our function compares two values, and the programmer, instead of the greater sign, used the greater or equals, or vice versa. Or think about loops. What if instead of starting it from 0, we started from 1? Because we don't remember is our array zero-based, index-based, or one-based? Also, what should be the last, the boundary of our loop? Should it be kind of items.length or items.length minus one, or maybe items.length plus one? I don't know any programmer who didn't do this type of a mistake at least once for each programming language they worked with. Finally, in addition to the looking at our system under test from the perspective of how it is supposed to work, we still need to take into account that it is a piece of software. It is using very particular programming language and a very particular data structures. And from that, we can we can find some additional classes of equivalence. For instance, think about the difference between long and integer data types in Java. When long is unsigned integer and the int can have sign. What if for the value that is supposed to have accept the negative values, we use long? Or what if we use negative values for the value that is not actually supposed to accept those? Think about our languages like JavaScript, where the numeric data type, like our number, can accept actually non-numeric values, such as plus infinity, minus infinity, not a number, or null. How our system will handle those values. So let's see in practice how we can use those test design techniques. Let's start from a pretty simple example. Consider that your child is applying for you are applying your child to American school, and there is a certain form that you fill, and you need to put the age of your child in a full years on September the 1st, and the system will use it to decide to which type of school your kid need to go. Is it elementary? Is it kindergarten, middle school, high school, or maybe they are not eligible to go to any school because they are toddlers? So here we have as many classes of equivalence, as many possible results our function can produce. So we can have, as a result, we can have invalid, so that for the values that are less than 0, your child can be ineligible. If they are 0, 1, or 2 years old, then for the pre-K, they can be 3 or 4 years old, etc. So first of all, we find the test data test inputs using the classes of equivalence. So for each output, we will take exact one value. Then we add the values on the boundary. And here is the entire set of test data that we will use to test this functionality. Looks pretty straightforward. Let's get a little bit more visual and also try to use 2 input variables instead of 1. Imagine we have a function that for some reason determines if one of the parameters is less than the other plus 1. So the b should be less than a plus 1, and the function takes a and b. So in this case, there will be exactly 2 classes of equivalence, one that produces results that are true, and the other that produces results that are false. And also we will have to take at least one point on the boundary, and it will produce false. So there will be just 3 data points, 3 sets of data that we will need to use. However, when we again think about the special values, we remember that the values can be both a and b can be negative, and we want to make sure that our function accepts both a positive and negative values. Also, we remember that 0 can be a special value. And this adds a big variety of additional test data points. We will have now 4 points on for just the boundary case. We will also have points in different points in each quadrant and on each of the axes. So when we introduced special values from 3 values, we went to more than a dozen. Let's try to analyze a little bit more complex and still a little bit artificial example from very famous book by G. Myers called Art of Software Testing. I think it was the first most popular book and most comprehensible about software testing. And actually, Myers suggested to use this example on their interviews for software testers. So imagine we have a function that takes 3 input variables, 3 parameters, each of them numeric, and each of those parameters represent one side of a triangle. And the function is supposed to tell you which type of triangle, if any, do those values represent. So it can be a triangle that have all the 3 sides that are the same. It's called equilateral. It can be the triangle that have 2 sides that of the same length and one other of the different, or it can be a triangle with all 3 different lengths of its sides. And finally, there are 2 cases when the values do not represent the vetted triangle. The first is if any of those sides are either less or equal 0. And the other when the sum of two sides is less or equal to the length of the other side. So now let's try to use the classes of equivalence to produce the test data for this functionality. So first of all, we need to identify which conditions are we testing. And if we think about the different conditions that we're testing and the different results that this function can produce, we realize that actually we can focus on testing the different cases of valid triangles. So depending on what relations between its sides there are. And for each of those, we will first make sure that the condition of relations between those sides is matched. And then we'll try to understand, is it a valid triangle or it is one of two subtypes of invalid triangles. So either with a negative or zero sides, or the sides where two of them, the sum of two of them is less than the third. So first, let's look at the equilateral triangle. So there is just one data point for, just one class of equivalence for a valid triangle here. We can use any value like 1, 1, 1 or 5.2, 5.2, 5.2. Frankly, I would use the second because it is a real number that has decimals, and we want this function to support those. Then we can check some inverted triangle scenarios. Here we will have just two of them. If the only side is equal to 0, or if it is less than 0. So we can take 0, 0, 0, for instance, and minus 1.2, minus 1.2, minus 1.2, or something like that. So far, so good. Just 3 test data points. Okay, let's look at the triangle where two sides are the same and the other is different. So here, the things are becoming a little bit more tricky. So first of all, for the valid triangle, there will be 3 different classes of equivalence. So we will have to do some permutations. So first of all, we check if the first, the case when the first side is equal to the second, but not equal to the third. Then first equal to the third, but not to the second. And finally, second equals to the third, but not to the first. So 3 points, not that complex. For the case when sum of two sides are less or equal to the third, again, there is just 4 different classes of equivalence, 4 cases. So 2 for the case when first side is equal to the other, and 2 cases when first side is equal to the third one. With inverted sides, it is a little bit complicated here, because we can have a situation when only one side is inverted, or 2 sides are inverted, or all 3 sides are inverted. And for each of those, we remember the permutations we have here for the valid scenarios. So it is, I didn't produce them here, but it is pretty easy to do, but you will have quite a bunch of them. And finally, the triangle with all the different sides. So there will be 4 different cases for the weighted scenario, because we're interested about in which side is greater or less than the other one. Why? Well, because it may affect how we will be checking that the triangle is weighted. So for classes of equivalence here, with inverted sides, the situation is similar to what we had here. So we will have to check the situation when one side is inverted, the 2 sides are inverted, and 3 sides are inverted. And in each case, we will have to do all the permutations. And finally, for the case when sum of 2 sides are less or equal to the third, we will have to check first situation when sum of first 2 sides are less than third, then that they are equal to the third, then the sum of first and third sides are less than the second, etc., etc. It is pretty easy to produce that best data, but again, there will be a lot of points here. So what is the conclusion here? That first of all, you can divide and conquer, that you need to approach analysis in such a way that you have deal with a minimal number of conditions each time. Second, that even for such a simple case, if we really want to cover all the different permutations that comes from this pretty simple actually are examples. We will have a lot of this data, and we will have kind of about several dozens, if not 100, of the test cases for this simple triangle scenario. So why we have so many? Do we actually need all of them? Well, remember, we are talking about our black box testing. We don't know what is inside the box. We don't know how the program works. So because of that, we are just using a very formal methods to identify the test data. It produces a little bit of an overkill. And frankly, when you are thinking about each of those scenarios, you may think, okay, so this particular scenario, which bug is it supposed to find? Is there any meaningful defect that this particular scenario will find? And if you think not, well, probably you can exclude this from the test set. However, again, there is a lot of analysis required, and it is pretty easy or frankly to mess up, to miss something, or to produce too many test cases that actually doesn't add any value. Still, the classes of equivalence and boundary values analysis are both pretty powerful methods, but they are not the only ones that need to be used that can be used to produce the test data for your test cases. Because again, in case of too many different input parameters or too many different conditions, or when we don't know exactly how our functionality is supposed to work, we can have actually problems identifying those classes of equivalence because there are too many of those, or because we don't really understand how the program works in order to identify those classes of equivalence. But that is the material for the other lightning talk. But today one is finished. And thank you all very much. It was a pleasure.